The Amani F2 is an FPGA development system designed to interface with the Arduino and its compatible shields. If for no other reason, the F2 is useful as an embedded logic analyzer, thanks to Altera's verification tool, SignalTap, available for free in the Quartus II development environment. At its simplest, the Arduino developer can seek the F2 on the Arduino and observe various output signaling. In a system prototype, the developer can include the F2 in their hardware stack and use it to monitor bus transactions between the boards. The F2 in this configuration is passive and will not interfere with bus transactions. Let's go ahead and start with a simple Arduino and Amani stack and use SignalTap to observe signaling in some of the various Arduino examples. Let's begin by opening Altera's Quartus II. Go to File, New Project Wizard. Go ahead and click Next. And create a new directory for your project. I'm going to call this SignalTap Demo. Select the folder, and I'll just name it the same as the directory. No need to add files. Under the Family and Device Settings, go to Cyclone 2 and choose the EP2C5 T144C8 device. That's the FPGA on the Amani F2. Click Next and click Finish at the summary page. Under File, click New, Block Diagram Schematic File. Under the Symbol Tool tab or button, choose the input pin and we're going to place 7 of these on the left side. As well as 6 and 6 of these on the right side. Essentially what we've done is we've laid down the PB, PD, and PC connectors of the Arduino. On the Amani F2, we provide full coverage of the PC connector, as well as full coverage of the legacy PB connector, and partial coverage of the PD connector. We've left PD0 and PD1 open for free UART communications between the Arduino and its USB chip. On newer Arduinos, you'll see the I2C pins on the PB connector. The F2 does not provide coverage for these pins. We'll go ahead and double click. Start naming the pins. Okay. And on this remaining pin over here, we're going to go ahead and connect the Amani F2 clock, which is a 64 megahertz clock on board the F2. Okay. We'll go ahead and name this block symbol file. and we will do the initial. First, we're actually going to go to Device, and Pin Options, and reserve all unused pins as input tri-stated. Once the compilation is complete, you're going to notice these warnings that the pins are not connected. And that's okay, because the F2 in this particular case is going to be a passive monitor. So let's go ahead and go to Project, Assignments, Pin Planner, and open up the Pin Planning tool. If you go to Amani64.com, go to Hardware, F2 FPGA Shield, you will see an XLS file called Pin Mapping. Go ahead and download that, open it, and you will see the Arduino to Amani pin mappings for the various Amani devices. We are interested in the PB, PD, and PC connectors for the Amani F2, as well as the global clock 0, pin 88. Go ahead and assign clock 64 to pin 88. That can be done one of two ways, either via the drop-down menu, or you can actually enter in the text manually. Repeat the process for every pin. Okay. Once completed, you simply need to click the X in the upper right. You do not need to save the file. And you've now assigned the pins in the block symbol file. Next, we're going to run the SignalTap 2 logic analyzer and instantiate that as part of our design. Go ahead and click on the radial on the right of clock and choose the clock 64 option. Sample depth, we'll go ahead and make it 1K to begin with. And double click to include the rest of the pins into our project. Save the SignalTap file to a name of your choice, .stp. Click Yes to include it as part of the current project. Exit out and recompile once more. So for this project, I'm going to use an old Arduino Duomilinova. And one of the things you'll notice is on the USB connector, I've placed a piece of electrical tape, and that is to protect the Amani F2's power supplies as it seats on the Duomilinova. Newer versions of the Arduino have USB micro connectors, and this is not a concern. So go ahead and connect the Arduino to the F2. Take the PIC JTAG USB Blaster compatible JTAG programmer and seat it in the Amani F2 JTAG programming port. For this demo, you will only need 2 USB cables. You'll need the USB mini cable for the PIC JTAG, and you will need a standard USB cable for the Arduino, or whatever Arduino you choose. You'll need the appropriate USB cable. Okay, so bring back the SignalTap 2 analyzer. In the upper right, choose the USB blaster. On the soft manager, find our sigtap_demo.sof and click the program button. Now your Amani F2 is configured with the SignalTap device. Let's go ahead and click the Auto Run Analysis tool. And you will see that all the pins, save for the PB5, are high. And to be honest, I don't know what's running on this Arduino. That's why we should do dry runs before we actually try doing demo videos. Let's go ahead and go to the Arduino sketchbook. Just use the blink sketch. Go ahead and upload that to your Arduino. Okay, now that we're done, if you look at the gap between the Duo Millinova and the F2, you can see the LED blinking. And let's go ahead and bring back SignalTap, and we can observe PB5 toggling. Now in SignalTap there are 2 ways to observe signaling. You can actually have a free running acquisition, as we did, and you can also do an acquisition where it fills the 1K buffer and then stops and displays what was recorded. However, in this particular case, we are running a 64 megahertz clock. Each of these ticks at the top of the screen, or at the top of the acquisition window, represent a single 64 megahertz clock tick. So when you're observing a 1 hertz LED, a 64 megahertz clock with a 1K buffer depth is not going to capture that edge unless you're really lucky. So in this particular instance, we're just going to go ahead and do a free running acquisition, and we can observe it in real time. Okay. The next fun experiment we can try is to go over to Arduino.cc and download the SD Fruit Ethernet shell. It's SDRFRETHSH, and go ahead and create a sketch out of that, compile and upload it to your Arduino. So what this shell does is basically creates a command base where we can toggle every pin, set that pin as an input or output, and also pulse width modulate the pulse width modulation pins. And so we'll be able to observe these interactions with the SignalTap 2. So let's go ahead and go over to our Quartus II environment. Now we are going to slow down our sample clock because the pulse width modulation is a lot slower than the 64 megahertz clock on the Amani F2. So let's go ahead and go into the symbol tool menu, and if you downloaded this project file sigtap_demo from modulesurf.net, then you will have in the project library here this clock divider. So let's go ahead and place that in the block symbol file, connect the clock 64 pin to that. And then add an output pin. And we're going to call this pin clock 1K. Go ahead and save that. Compile the project. Upon completion of the synthesis, we're going to go back into the SignalTap tool. We're going to choose the 1K pin as our clock source. We're going to save it and recompile. Again, after compilation, we're going to reopen our SignalTap 2. We're going to program the F2 with the soft file, and we're going to do the free running capture. So now what you see coming up is all of the pins except for pin 5 are in the high position. So if we bring up our fruit shell, we can set pin 13 as output and write a 1 to pin 13, and you'll see PB5 goes high. Okay, so next we can toggle various pins. Etc. What we can also do is do the pulse command as such. And what we're doing is we're essentially enabling the pulse width modulation of the various PWM pins. And in the fruit shell, assigning a 1 to pin 9 means you're assigning the average equivalent of 1 volt. So for example, if we set pin 9 to the pulse value of 2, you see our pulse widens, which ups the average of the pulse width modulation. Again, we increase the duty cycle again. And there we go. So next I'd like to show you monitoring a live data bus. And in our particular case, we are going to monitor the SPI bus. So in our Quartus II environment, let's go back to our block symbol file. And let's just go ahead and eliminate the PC pins, the PD pins, and PB1 and 0. And we're going to keep these 4 pins as our S clock, MISO, MOSI, and chip select. And we're going to go ahead and get rid of our clock divider and we'll keep clock 64 just in case we need it. So you notice when you change the names of the pins, the pin assignment goes away. So first thing we'll do is we'll compile and then we'll go back and reassign the pins. Let's go ahead and go to Amani64.com. Click on Open IP, Block Symbol File Library. Actually, we're going to click on Code Library. We're going to scroll down to the SPI P-Port Checkout demo code. Now this is the standard hello world code that I like to use when interfacing the F2 or any type of Amani board with the Arduino. And essentially what this does is it does SPI transfers from the Arduino to the Amani, which then converts those to parallel data and feeds them back to the Arduino. And so basically it's exercising pins between the two boards and it's checking communications between the two boards. And it's a simple checkout when bringing up both boards together. So in this particular case, we're just going to download the Arduino code and observe simple SPI transactions as generated by the Arduino. So here you see the Arduino sends out an increasing byte count. Sends it over to the F2, in which case if we were to actually upload the F2 image, the SPI P-port image, the F2 would convert this to parallel data and send it back. However, we do not have that image installed. We have the SignalTap monitor installed instead, so we are getting error counts. So let's go over to back to our Quartus II. We're done compiling. Let's go ahead and assign the pins to our pin planner. Let's delete the unused pins designated by a question mark. So in the SPI_P-port software, I have the 4 SPI pins defined. So going back to our Arduino pin map, we can find PB2, 3, 4, and 5 here. And we'll just go ahead and assign those pins. So our shift clock is PB5, which translates to pin 104. Our master output slave input is PB3, that's pin 101 on the Amani F2. Our master input slave output is pin PB4, which is pin 103 on the F4, or I'm sorry, the F2. And the chip select is PB2, which is pin 100. Okay, so we can go ahead and close that and recompile. Click OK. Let's go back to our SignalTap. Go to our setup. Delete those. Let's go to the node finder for the clock entry. Go to pins all. And in this case we are going to use the shift clock as the clock for our logic analyzer. And for this side of the house, we are going to monitor the MISO, MOSI, and chip select. Save that. And once again, we will compile. I should mention that we could have saved one compile cycle in there by actually doing our SignalTap modifications prior to the actual pin assignment. Let's go ahead and program the Amani F2 with the new image, and let's perform a free run. Okay, so here we see SPI transactions in progress. So we're going to actually do a single capture and investigate what's happening. So the first thing we'll mention is that every tick at the top is a shift clock tick. So the master input slave output pin is always high, and that's because the F2 is using that pin as an input. It's not actually sending data back to the Arduino, which we'll change in our next step. The master output slave input pin we can see is toggling. So what we don't see is the chip select pin toggling, which is actually expected because the chip select is an active low signal that the shift clock only operates during the active low cycle of the chip select. If you go back and look at the Arduino sketch. So actually including the chip select as part of this capture is not very helpful. But we do see the multi-line toggling. So that's pretty good. Let's make it a little bit more meaningful and start to explore the programmable logic aspects of the F2. And let's actually drop in the accompanying Amani file for the SPI P-port project. So go ahead and download that by clicking the Amani file. If you don't want to do that, you can actually go to Open Cores and download the SPI_receiver.zip. And let's copy that to our project directory. And we can extract it here. Okay, so you'll see it drop the .v and block symbol files in. Go ahead and close that out. Close that out. Let's go back to our Quartus II environment. We can go to the symbol tool menu. Go to the project, and now we have a SPI receiver inserted. And if we double click that, we can see the RTL that is needed to receive the SPI bus data and convert that over into parallel data. So we're going to connect our clock 64 to clock 32. Don't worry about connecting a 64 megahertz clock to a 32 megahertz clock input. I should go back and make that generic. And then we're going to change our S clock and connect it here. I'm going to take the MOSI. And once more for the chip select. For the MISO, we're just going to go ahead and wire that up to the MOSI. As a type of loopback. The actual SPI P-port code on the Arduino does not error check the MISO line. It only checks the parallel data. So next we're going to take an output pin. In fact, we need to change the MISO to an output pin. Output. So we'll go back and change this to MISO. And we're going to define a bus P data 7 down to 0 on this particular pin. And so what you'll see is an actual bus here instead of the standard wire. Okay. Let's go ahead and save that, and we're going to recompile. Then we'll go ahead and set up our SignalTap logic analyzer. So we'll go back to setup. And again, we're going to trigger off the shift clock, and now we're going to add the parallel data bus as well, and that'll show us bits 0 through 7 of that bus. So we can go ahead and save that, X out, and next we need to assign our pins. Okay, so master input slave output was actually retained, even though we changed the direction. All we need to do next is add the 8 pins for the parallel bus. So if we go back to the Arduino sketch, you'll notice that our parallel bus pins are defined as PB 0 and 1, 2, 3, PD 2 through 7. And what we're actually doing here, let's see if I can pull up the Leonardo, for example. We're actually using pins 2, 3, 4, 5, 6, 7, 8, 9 as the parallel data bus. This being pin 2 of the Arduino being parallel bus 0, and pin 9 of the Arduino being parallel bus bit 7. And the reason why we're not using pins 1 and 0 is because A, the UART communicates over these 2 pins, and B, the connectivity is not there on the F2 because I always wanted to make sure that the user was able to use the UART and didn't suffer the frustration of accidentally programming these two pins to a logic level high, for example, and not getting communications with their Arduino. So, that being said, let's go back and assign these 8 bits to pins 2 through 7, PD2 through 7, and then PB0 and PB1. And we'll start at the top. Okay, it's that simple. Go ahead and X out. Let's bring back Quartus II and go ahead and recompile once more. Okay. Now that we're done with our synthesis, let's go back to the SignalTap 2. We're going to go ahead and load the image onto the F2. And before we hit go, let's go back to our Arduino monitor and notice that the Arduino code is still running. It's still generating the 8-bit pattern, and it's still doing an error check. So let's go ahead and hit reset real quick, and let's reset that error count. And you'll notice already that the error count is now 0. And why is that? That's because we've gone ahead and already uploaded the FPGA image that has the SPI receiver that translates it back to parallel data, at which point the Arduino reads that parallel data back and compares it to the master output slave input. So that's good news. And just for fun, let's go ahead and capture a frame of that data. And here we see the new entry, parallel data. If we can expand that, we can actually see that that very parallel data being shifted in from the master output slave input. And we also see the MISO line is reflecting exactly what the MOSI line was inputting to the Amani F2. So if we zoom in on the parallel data, we can actually see the byte format of this data being shifted in. Now what would be nice is if I actually included a framing bit for the logic analyzer to actually know when the framing is completed. And that's something that you know, the user is free to work on at home. Okay, so next we're going to experiment with the color LCD shield from SparkFun, and we're going to use a sketch called Cascada from a Lee Klotz. I apologize if I mispronounced your name. This is actually a very creative sketch that does an FFT on incoming signals over the analog inputs of the Arduino, and then the actual FFT is displayed via the LCD shield. So we're going to turn off, remove power from the stack, and actually we don't need to separate the two. We're just going to stack the LCD shield on top of the F2, like so. And so we'll go ahead and plug the bit JTAG programmer back in, and we're going to plug the Arduino back in. Let's go ahead and load the Arduino sketch. And I do apologize that the LCD screen is upside down currently. We do need to go ahead and remove the parallel output data. Features of the Arduino. We'll go ahead and put the input pin back for the MISO. And then we'll recompile that. So if we go over to the SparkFun website and go to the Color LCD Shield product page and download the schematic, we can see a few things: that the S clock and the master output slave input pins are still the same. They're not using the MISO line, and the pin 8 is being used for a reset for the LCD, and the actual chip select line is not D10 but is actually D9. So in that particular case, I don't really care about the LCD reset, nor do I care about the chip select line. So we're not going to include that in the logic monitor. What we are going to include, though, are the these 3 push buttons, D3, D4, D5. So we'll go ahead and hook those up. So let's go ahead and reopen. So what I've done is I've set up the F2 schematic file to reflect the pins of interest of the LCD shield. If you remember, we were interested in the master output slave input, the shift clock, as well as the 3 push buttons. And then I went ahead and set up the pin planner, as well as set up the SignalTap logic analyzer for the pins of interest. So we'll go ahead and load the image, and let's monitor what's going on. So here we see no action on the MISO line. We do have a repeating pattern on the MOSI line. The chip select, as expected, is quiet. So let's go ahead and over and turn on the other camera. Apologize, one sec. And see what's happening with the LCD display. So I'm already noticing that here we have we pushed the switch number 3, and switch number 2. Let's hold down switch number 1. Okay. Switch switch 2. Does not seem to be being picked up by the logic analyzer. And switch 1. So you can see that I'm changing some of the attenuation settings. And the bandwidth settings. And we can see the transactions taking place on the logic analyzer. Okay. And at the very bottom we see the noise floor starting to come in. Let's zoom out and see those transactions taking place on the MOSI line. So that those transactions there are actually telling the LCD display what to display on the actual noise floor and the waterfall. And of course, it's if I remember correctly, it's every one of those transfers represents an actual pixel, color, etc. So that's an example of how to embed the Amani F2 into a prototyping stack and monitor bus transactions, signaling, etc. Certainly you're not limited to SPI bus transfers. There's I2C, there's parallel bus data transfers, all sorts of different protocols that you can monitor with your logic analyzer. And I'd also like to point out that again that the F2 is not intended to be only a logic analyzer. It's also intended to be a standalone controller or a complementary controller with the Arduino and its associated shields. In this particular setup, you can see that the F2 is embedded in the middle of the stack. That doesn't mean that it's compromised. There are 16 I/O available to the user out the front of the F2. That, for example, you can use this particular DAC PMOD from Digilent, plug it into this connector, and you can now send analog data out. Or if you're using this Cascada FFT spectrum analyzer, if the Arduino does not have the bandwidth that you would like to perform wide enough bandwidth signals, certainly you can take one of the A to D PMODs, plug that into the F2, and actually do the D to A processing on board of the F2. Collect samples. You can now either drop in a FFT core into the F2 itself, or the F2 can hand it off to the Arduino to do the Fourier analysis on that, which then would hand it over to the LCD shield for display. I mean, the possibilities really are endless in this scenario. I mean, you may not even want to use the Arduino. You may want a high bandwidth A to D with an FFT core on the Amani F2, and the Amani F2 is capable of actually handling the SPI transactions to the LCD shield. So I hope you enjoyed the demo. If you have any questions, feel free to email me. My email's at the bottom of the screen, and I thank you for your time.